What's cooking, y'all? Welcome back. In this video, we're going to talk about equivalent propositions. We say two propositions are equivalent if and only if they have the same truth tables. Let's take a look at our first example of such an equivalent proposition, which is we have this proposition P, which can either be true or false. Of course, we know that not P inverts those values. So when P is true, not P is false. When P is false, not P is true. One equivalent proposition for P is not P. Specifically, we can test this in MATLAB. Let's go ahead and set P equal to a logical vector. And in this case, it will be a non-scalar vector. Perhaps we store it as a logical row vector. Let's go ahead and test not P actually inverts that, and then not P inverts that. Of course, this leads to an infinite chain of knots. So anytime we have an even number of knots, it refers back. Point of this is that there are an infinite number of logical propositions. One of the fun things about computer science is, can you get it to a minimum number? So we probably would not use not P because P is a better way to do that. Similarly, we can avoid other situations where we have equivalent propositions in different forms. Let's take a look at yet another example. Remember, in a previous video, we talked about P and Q, which was the AND operation true only when both are true. We then defined a NAND operation, which was not AND, that inverted the output of AND. So everywhere there's a 0 becomes 1. Everywhere there's a 1 becomes 0. Notice that we have an equivalent version of NAND by doing not P or not Q. Specifically, we can actually check this. Not P is true when P is false. So 0, 0, 1, 1 becomes 1, 1, 0, 0 when I not it. Similarly, 0, 1, 0, 1 becomes 1, 0, 1, 0. Remember, the OR operation is true when at least one of the inputs is true. So if I take not P or not Q, that will be true only when at least one of the inputs is true. When I look at not P, then not Q, let's take the OR operation. 1 or 1 becomes 1. 1 or 0 becomes 1. 0 or 1 becomes 1. 0 or 0 becomes 0. In other words, not P or not Q is equivalent. It's an equivalent proposition to the NAND operation, P NAND Q, or not P and Q. Of course, we could check that in MATLAB. Let's go ahead and create the P and Q columns. We could actually create this entire matrix just like we've done before. P, Q, P and Q. Then let's take not P and Q, which is the NAND operation. Then we'll actually do not P. Then we'll do not Q. And then finally, we'll test this little OR operation on both of those for an equivalent version of NAND. So this would be not P or not Q. When I push enter, notice the output of this array is identical to the output of the table. In other words, columns 4 and 7 have identical output. Those two propositions, the NAND proposition and the not P or not Q proposition, are equivalent because their truth values are equivalent. We're not going to dive too deep into the ramifications of this. There is a very, very famous problem in computer architecture, which is to figure out how many gates we need to actually create in our computer architecture. One thing I haven't mentioned in any of these videos is every logical operation can be actually implemented in hardware using transistors. The corresponding gate, the corresponding hardware that implements each of these would be called an AND gate, an OR gate, an XOR gate, a NOT gate, an XNOR gate, etc. One of the problems in computer architecture is to determine a minimum number of gates needed to create an entire logical structure for computers to work on. There is a famous result that says you can create every logical operation using just NAND gates. That's kind of a funny thing because it means that your computer architecture can be simplified into a minimum number of gate types. One of the problems of designing a computer is to figure out which gates you want. This is a brief introduction into that much larger world. We're not going to focus so heavily on that in MATLAB coding. I did want to mention it because it's a fun story to know about. One thing that I will say is sometimes when we create checks for if statements, it's useful to know about equivalent propositions to simplify our code. One of the themes of this class is to make your code as easy to read as possible. And this is one mechanism that we can do that. create simple check propositions so that people that are reading your code don't have to recreate the wheel or spend hours and hours and hours figuring out what your operation is doing. That ends our introduction to the first of the 4 purposes that we use logical data in MATLAB for. Remember, those 4 were to perform logical operations, to perform relational operations, to test the state of MATLAB variables, and to address or find special entries in arrays. We have now just run through a plethora of different logical operations. Those included NOT, AND, OR, XOR, NAND, XNOR, and NOR. We've also seen how to combine those. We've talked about compatible sizes. We've talked about equivalent propositions. We've talked about terminology to refer to the sizes of logical data. This was an action-packed lesson. We are going to now use the information that we've generated talking about logical operations to kind of inform the way that we talk about the next 3 of these, which is to perform relational operations, to test the state of MATLAB variables, and to address and find special entries of MATLAB arrays. Very nice work. I'm so proud of your hard work and effort. When we work hard, reflect on our learning, make mistakes, and stay dedicated, our brain grows bigger and we develop new technical skills. As a friendly reminder, I always welcome your questions and comments in the comment section below. Thank you so much for your attention. I'll see you in the next sequence of videos where we're going to talk about performing relational operations and how those relate to the logical data class. See you there.